So in the last video, I said that in this video we were going to talk about ints, but I've realized that for everybody to understand what I have to share about ints, you have to have a solid foundation, a solid understanding of how computers work. So if you already understand binary and circuits and coding schemes and bytes and kilobytes and megabytes and gigabytes and terabytes, and if you understand how all of that works already, you can skip this video. What we're going to learn in this video is we're going to learn how computers work, and specifically the takeaways from this video will be you'll understand circuits and switches by the end of this video. You'll understand coding schemes, binary digits, something that's 2 to the power of n and how that plays into everything. We'll take a brief look at the 5 generations of computers, Moore's law, bits, bytes, kilobytes, megabytes, gigabytes, terabytes, how we measure bits, and also what machine language means. So we're going to see all of that in this video. And generally I like to talk about this in a free form way, but I found that having some structure of slides, generally when I present, I like to be free form, but having structure of slides in this presentation helps students learn the material. So I put together a couple of slides here to walk us through it. So the first thing you need to understand about how computers work is totally self-evident and obvious, and even kind of funny just even to say it, but computers run on electricity. But that's really an important point because electricity has 2 discrete states, on and off. Electricity can be on or off. And because electricity can be on or off, we could take those 2 discrete states and we can assign a coding scheme to whether or not the circuit, the switch, is on or off. Here's an example. Take your porch light on Halloween. That is a circuit, that's a switch. And that circuit, that switch, can be on or off. And there is a coding scheme associated with the porch light, in America at least, on October 31st, Halloween. And the coding scheme associated with that porch light on Halloween in America is that if the circuit, the switch, is in an on position, it means come trick or treat. And if the circuit or the switch is in an off position, so if the light's off, it means go away. Don't come trick or treat at this house. So we have a circuit or a switch, and we have a coding scheme, and based upon whether or not that circuit or switch is on or off, it means one thing or another thing. So that's like really the foundation, the fundamentals of how computers work. And all you have to do is take that simple example and scale it up several billion times, and you have like the greatest computer processor ever. That's the foundation of how it all works. It's just you got circuits, they're in some state of on or off, and the arrangement of those on or off switches, those on or off circuits or transistors, all of those words are interchangeable, circuit, switch, transistor. The arrangement of the on and off has some meaning. It's associated with some coding scheme. That's it. That's how computers work. So we assign meaning to the on or off state. The porch light on Halloween example, if we have one porch light, we could have 2 messages. We're going to explore this a little further now. One porch light, 2 messages. How many messages can we have if we have 2 porch lights? We could have 4. Our coding scheme could have 4 messages, right? One porch light, if it's on, come trick or treat. If it's off, go away. That's 2 messages. 2 porch lights, right? We could have 4 messages. They could both be on and that can mean something. They could both be off and that can mean something. This one could be on and this one could be off and that can mean something, and vice versa. And this can mean something too. So 4 different messages, right? Those 4 different messages could be associated with those 4 states, those 4 arrangements of on or off. So what about if we had 3 porch lights? We could have 8 messages associated with the on-off states of those 3 porch lights. And the formula for figuring out how many combinations of on or off are there are 2 to the n, where n is the number of porch lights, or circuits, or switches, or transistors, whatever you want to call it, where n is the number of porch lights. So 2 to the 3 is 2 times 2 times 2 is 2 to the power of 3. 2 times 2 times 2 is 2, 4, 8. And then what would it be if we had this many porch lights? So pause the video right now and figure it out. And if you figure it out, so I'm going to go on now, if you figure it out, you'll find that you'll hear numbers which you have always heard with computers. 2, 4, 8, 16, 32, 64, 128, 256. Those are numbers we have always heard with computers. and they're all base 2. It's base 2 because on or off, there are 2 states there. It's binary. Binary means 2 choices. Bi is the prefix, which means 2, which is why bicycle is like 2 wheels, bicycle, bi. Or biplane is 2 wings, biplane. Or bisexual is 2 options, bi, right? Bi means 2, bi means 2. And so the base 2, bi, right, binary, and then however many you have gets the permutations of possible combinations. So 2 to the power of 8 gives you 256 messages. So just pause this video and say back to yourself, if you're just learning this, pause this video and say back to yourself everything you just learned. And what you should have said back to yourself is that computers run on electricity. Electricity can be on or off, and then based upon the state of like a circuit, one porch light in this example, the Halloween example, based upon the state of that circuit, we can associate a coding scheme with the states of on or off. If it's on, come trick or treat. If it's off, go away. If we had 2 porch lights, 4 messages. If we had 3 porch lights, 8 messages, so on and so forth. The arrangement of on and off allows us to associate a coding scheme. That's it. That's computers. And so here's an example of a made-up coding scheme. We get to create the coding schemes as humans. We could just say, hey, this arrangement of on and off, it means this. And so if I had 2 porch lights, here are the 4 possible messages that I could convey. And instead of writing, oh, I did a little bit of a jump there. Hold on one second. I like that, but I'm going to jump down to this one here first. Instead of writing on and off and all that stuff all over, we could abbreviate those with 0s and 1s. We could abbreviate them with 0s and 1s. So we could say 1 represents on, just arbitrarily, because I don't want to have to write on and I don't want to have to write off. I'll just write 1 for on and 0 for off. So instead of writing that 1 and 0 over and over and over, I could just do 1, 1, 1, 0, 0, 1, 0, 0. And now you know why so often when you look up graphics of things related to computers, you see a bunch of 0s and 1s. The 1s mean on, the 0s mean off. And as a matter of fact, that power symbol, which I've put up in the top right corner of the screen here, that power symbol represents a 0. You can see that 0 right here, ba-doom, and a 1. It represents on and off, which is exactly what a power switch does. It turns things on or off. Pretty amazing. Now you understand how computers work. Computers run on electricity. Electricity has 2 discrete states, on or off. Based upon the state of a circuit, like the porch light on Halloween, we can associate messages with that state. So if we have 1 light, on means come trick or treat, off means go away, and that's called a coding scheme. That's called a coding scheme. Now instead of having to write on and off over and over and over, we'll just abbreviate that as 1 means on and 0 means off. That's it. That's how computers work. That's the foundation, the fundamentals, but that's really the essential principle of how computers work. That's the essential principle. It's kind of mind-blowing it's that easy. So here's just another example of a coding scheme I made up. I'm going to allow these arrangements of circuits in an on-off state to represent different letters of the alphabet. So these 3 offs, 0, 0, 0 will represent A, 0, 0, 1 will represent B, so that's off, off, on, if we were to actually look at the state of the circuit. And so now I could have you translate, right? I could have you translate some message which is stored in binary. And so those 0s and 1s here, I want you to figure out what they are. So pause the video and figure it out. Did you get it? So this is what it is. So 0, 0, 1, when circuits are in a state of off, off, on, that's the letter B. And then that's the letter A when they're all off. And when we have 1 on and then 2 off, that's D. And so I have bad cab. That's all I could come up with the first 3, 6, 8 letters of the alphabet. That's all I could come up with. But that's an example of coding schemes and how if we had circuits stored in an arrangement of on and off, we could use a coding scheme to translate those to letters of the alphabet. Pretty amazing. All right, so we already saw this and we saw that, and now we're going to learn about binary digits. So those 0s and 1s are referred to as binary digits. A single 0 or a single 1, that's a binary digit, a singular. Binary digits would be multiple. And binary digits is where we get the abbreviation for bits. So I'm sure you've heard that computer bits, right? Bits, that's where we get bits. And so that's that thing there. So bits, that's it. I just want you to know about bits. And when we get to the end of this video, or a little bit further in the video, we'll look at how do we measure bits. Okay, so here's just a little terminology disambiguation. On and off, 1 and 0, binary digits, bits, and machine language are all words used to refer to this idea that within a computer, it's all nothing but a bunch of zeros and ones or switches that are on or off. It's all just a bunch of binary digits or bits. That's the language which computers speak. It's machine language, right? So you hear all those phrases, but that's what they mean. It's all just referring to circuits which are on or off, okay? And then circuit switches, transistors, and even gates are all words used to refer to this thing within a computer that can either be on or off. It's a circuit, it's a switch, it's a gate that can either be opened or closed. It's a transistor. You will learn that people use all of those words to talk about the same thing, this ability of computers to store on-off states. So coding schemes. So you saw me make up a coding scheme for text, but a coding scheme that has been widely used for text in the past and is still a part of the most popular coding scheme in the world today is ASCII. And so ASCII, if we went and looked at ASCII, and we'll just go ASCII wiki, we will see that ba-doom, ba-doom. We will see that all the way down here at the bottom of this ASCII page, right, that we have letters of the alphabet, and those letters of the alphabet are associated with ones and zeros. Like how amazing is that, right? So that if we have these switches, these circuits, in this arrangement of on, off, 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 on, that's capital letter A. So literally when you hit the capital letter A on your keyboard, somewhere within your computer, 7 circuits and switches go into that arrangement of on and off. Pretty amazing. It's actually truly mind-blowing because your computer can reference all of those switches and see them so quickly and understand and be able to display colors and text by just looking at them like instantaneously practically and bringing back what they represent and then showing that on the screen. It's truly amazing. So the most popular coding scheme today is UTF-8. And if you Google UTF-8 wiki, you will come to this page here and you'll see this graph and you can see the death of ASCII, right? Played a role at one time but no longer worked because people are using different coding schemes around the world and we needed one to encapsulate all the languages of the world. And so the same people who created the Go programming language were the people who created the world's most popular coding scheme, which is now UTF-8. And the first part of UTF-8 encapsulates and incorporates ASCII. So the first part of UTF-8 is ASCII, which is cool. So the next thing I want to show you is measuring bits, and then we'll take a little look at the history of computers, and then we'll call it good. So measuring bits, if you have a single binary digit or a single bit, that's just called a bit. If you have 8 bits, that's called a byte, B-Y-T-E. If you have 1,000 bytes, that's called a kilobyte. Now really, it's 1,024 bytes, but it's just easier to kind of think of it as 1,000. So if you have 1,024 bytes, that's a kilobyte. If you have 1,000 kilobytes, that's a megabyte. If you have 1,000 megabytes, that's a gigabyte. If you have 1,000 gigabytes, that's a terabyte. So if you do the math on that, if you have like a 500 gigabyte drive, you could actually back it out and figure out how many single zeros and ones that drive can store, which is pretty phenomenal. All right. So we started out with the porch light on Halloween analogy, and that's really pretty close to the truth as to how computers work. And the first electronic computer, they really sort of came into being in the 40s, 1940s. And the first one was the ENIAC. And then after that, they had the UNIVAC. But the ENIAC was built to help calculate trajectories on shells shot from ships at sea to the land during World War II. They need to be able to do that more quickly and take into account factors like temperature and humidity. And it had 16,000, to use our analogy, had 16,000 porch lights, 16,000 lights, which could be arranged in different orders of on or off. And they could be checked, which ones are on, which one are off. But instead of using light bulbs, they used vacuum tubes. So you could also call these circuits, right? They were circuits. They were either on or off. And the first generation of computers used vacuum tubes to store those on-off states. The problem with that was that vacuum tubes ran hot and they burned out and they attracted moths. And so Grace Hopper, you know, was one of the original female computer scientists. And so here is a picture of Grace, and there is, let's just see if this gets the full page. No, let's go to this one. All right. So here is a picture of a moth that they pulled out of the computer, and it was taped into this book, and you can see it's the first actual case of a bug being found in a computer. And so they called it debugging the computer, to go into the computer and pull the bugs out when they short-circuited around the vacuum tubes. And that's where our phrase came from, debugging computers. So that's the first generation of computer, right? It was it ran on vacuum tubes for the on-off, storing the on-off state. And they were hot, and there's only 16,000 of them. The second generation ran on transistors, which didn't burn out and which were cool. And they were a lot smaller. And so the second generation computers had transistors, and that stored the on-off state, which could be checked. The third generation computers used silicon wafers or integrated circuits. And so if you zoomed in on this image, you would see a whole bunch of tiny little squares, right? Like here's a little square, here's a little square. And those are each silicon wafers. Those are each chips. And they're about the size of my thumbnail or smaller, and about the thickness too. And that's what in the third generation was able to store the on-off states. And if you look at the growth of how many circuits they could get onto a silicon wafer, so microprocessor, transistor count, circuit, transistor, whatever you want to call it, tomato, tomato, it's the same thing, right? If you look at how many they were able to get onto a silicon wafer, back in 1971 they had 2,300. In the 80s they had like maybe 30,000. In the 90s they had like maybe, you know, 700,000 in the 90s. In 2000, they had maybe 10 million. Wow. 10 million on-off circuit switches, which could be set into an on-off state, and they could be checked almost instantaneously, and it's all stored on something no bigger than your thumbnail. That's amazing. In 2011, we're talking more like 2.6 billion on something the size of your pinky fingernail. Truly amazing. 2.6 billion. That is unreal, 2.6 billion. So that's the third generation, was a silicon wafer, the integrated circuit. And by the way, Intel stands for integrated electronics. Some people think Intel is for, hey, it's for people who are intelligent. And that's a great association for the company, but Intel stands for integrated electronics, which is about, you know, integrated circuits and chips. All right, so that's the third generation of computers. And then the fact that they progress so quickly, where it doubles every 18 months to 2 years, the number of circuits on a chip, that's called Moore's Law. And so that's something that Gordon Moore, one of the founders of Intel, said back in the 60s, and it's held true. Started to taper off a little because, wow, how do you double from 2.6 billion to, what would that be, 5.2 billion in 2 years? It's starting to taper off a little, but still the processing and speed, it's holding pretty close to doubling every 2 years. So that's the generations of computers. Some people say, what is the fifth generation of computer? I'm gonna leave that up to you. Nobody's agreed on what the fifth generation of computers are. I'd say it has something to do with interconnectedness and networking and AI. I'd say that's the next big generation of computing. So one last thing that we have to learn about, which we'll learn about in another video, and there'll be other things to learn about, is our numeral systems. Numeral systems. And so numeral systems are how do we count numbers, and how do you do that in binary? And so that's something that's super interesting, like hexadecimal or decimal or binary. How do we store numbers using just the binary number system? So that's how computers work. And you needed to understand that because in the next video, we're going to talk about int, and we'll talk about a byte. And I want you to understand what a byte is, that's 8 bits, and that translates back to 8 circuits in some on-off state that are being stored somewhere. Because Go is about creating programs which are performant and which natively take advantage of the machine they're running on. So understanding like the different data types and how they use memory and how memory is being used, and that's really important and helpful. All right, so that's a little bit about how computers work. I hope that was mind-blowing for you because when I first learned it, it was mind-blowing for me, and it's truly one of the marvels of the human species. One of the amazing things that we've been able to accomplish is creating these incredible machines. A couple of good movies, or one good movie that comes to mind for me, is a movie about Alan Turing called Bletchley Park. Alan Turing, Bletchley Park. And so that's another great little insight into the history of computers. I'm just going to see if I could find the movie. Alan Turing, Bletchley Park movie. I'm going to type in movie and see what comes up because I'm forgetting the name of the movie here. We'll go to all. And The Imitation Game. The Imitation Game. That was the name of the movie. So check that out if you haven't seen that. That's a pretty cool movie. All right, or at least go watch the preview. Go watch the trailer. Cool. Next video, we're going to talk about numeral systems. No, we're going to talk about ints.